Iridium is a transitional metal which is located in the middle of the periodic table below rhodium. If we take a look at the prevalence of all the elements in the Earth's crust, iridium holds the last place. That is, billions of atoms of all that there is, and only one atom of iridium. This metal is 40 times rarer than gold. In much higher concentrations, iridium is found in meteorites and also in the depths of the Earth, in magma. Interesting, though, in the layers of rock sediments, through most precisely in the formation of clay that is aged about 66 million years, there were found high concentrations of iridium, and this can indicate the collision of Earth with a huge meteorite in the past, which in theory was the cause of the deaths of the dinosaurs. In appearance, iridium is a shiny metal that does not oxidize in air. This metal has almost the highest density of all metals, just 0.12% lower than that of osmium, the most dense metal. In this tiny, tiny metal droplet, which is the size of a match head, we have 1 gram of iridium to help you understand how high the density is of iridium, shown other metals with the same mass for comparison. Lead, copper, gallium, zinc, magnesium, and the lightest metal, lithium. The volumes of the first and last metal differ by about 30 times, although their mass is the same. Iridium is also a very hard metal that is firmer than the solid steel. 1.5 times. Iridium is additional to its rarity. It's the most stable metal that does not oxidize in air, up to 2,000 degrees, and is not soluble in either acid, aqua regia. Iridium can only react with fluorine at the temperature about 600 degrees.
So the formula to finding half-life would be half of the original number equals original number E to the power of KT. For iridium, the original number would be 192 and then T would be 73 days. So it would be half 192 equals 192E K 73. And so 192 divided by 2 would be 96, and then it would be 96 equals 192 e to the power of k 73. And then you would divide 192 on both sides, and on the left side you would get 0.5 and then equals e power k and then 73. To get rid of E, you would have to put ln on both sides, so ln would cancel out E, and then you'll be left with ln 0.5 equals K 73. Then you would divide 73 on both sides, and then you would get that K equals negative 0.0094, and that's what K is. So if you were to graph this, you would only use the right side of the equation, which would be 192e to the power of k 73. But instead of t, you would put x, so it would be 192e to the power of negative 0.0094x. And if you were to put that in a graphing calculator, you would get a negative slope, the graph would be going downwards, which is what you're supposed to be looking for. So let's say we're going to try to find 20% of the equation. So instead of 50%, which is half-life, I would put 20%. So if I were to do that, I would put 0.2 equals e to the power of negative 0.0094 and t. So then I would put ln on both sides to cancel out the e, and then it will be ln 0.2 equals negative 0.0094t. Then I would divide 0.0094 on both sides, and then I would get exactly 171.2167992. But we could just round the whole number to 171. And this will be the new T. In conclusion, Iridium 192 is a useful element that we use in commonly found resources like spark plugs, and it has an interesting compound on how it's created and formed. And its half-life is extremely short.